We spend billions building massive data centers to pre-train artificial intelligence. But once that initial training is complete, the model faces a different bottleneck: the isolated, iterative process of thinking through a single problem at inference time. Historically, AI systems lacked the internal architecture to navigate complex, open-ended search spaces on their own. They required human engineers to step in and hard-code the rules of deduction using handcrafted heuristics. Heuristics are mental shortcuts or rules of thumb used to make decisions and solve problems quickly. Look at early milestones in game playing and reasoning. Programs like Deep Blue or even early versions of AlphaGo relied heavily on databases of human matches or domain-specific logic to navigate their environments. This approach evolved into neuro-symbolic systems. Researchers would take a standard language model and wrap it inside an explicit human-coded symbolic deduction engine to force the machine to follow strict logical rules. This highlights the core challenge of inference-time compute. To make a model spend more computational power before answering, it needs a structural framework to think within. The bottleneck in early AI reasoning was that human engineers had to manually write the exact logical pathways the machine was allowed to explore. That architecture is now changing. Recent developments, specifically the OpenAI O-series models, move away from domain-specific rules and instead scale general-purpose reinforcement learning. Reinforcement learning is an area of machine learning where an agent learns to make decisions by performing actions and receiving rewards or penalties. By scaling this reward-based training, models internalize heuristic search strategies directly into their weights. The external, manually coded wrappers become obsolete. The ultimate testing ground for this theory is Codeforces. It is a highly constrained, objectively gradable competitive programming platform where top software engineers solve complex algorithmic puzzles. This chart tracks the Codeforces ELO rating climb of various models. An ELO rating is a system for calculating the relative skill levels of players in zero-sum games. The jump from the O1 model at the 89th percentile to the O3 model at the 99.8th percentile places the AI in the absolute elite tier of global competitors. The data suggests that complex algorithmic reasoning no longer relies on engineers building better heuristic wrappers. It relies on teaching the model to autonomously generate its own search trees. Consider the constraints of the 2024 International Olympiad in Informatics: 6 highly complex algorithmic problems, a strict 10-hour time limit, and a hard cap of 50 submissions per problem. To compete, researchers deployed the O1 IOI pipeline. This was a fine-tuned system wrapped in highly complex, hand-engineered test time strategies designed specifically for this event. First, human-written scripts divided problems into subtasks, and the system sampled 10,000 candidate solutions. Next, scripts clustered these solutions based on their outputs. Finally, a re-ranking phase used a scoring function to penalize and filter out clusters that failed public test cases. Finally, a round-robin submission process selected the best 50 candidates from the highest-ranked clusters. The result of this highly orchestrated process was 213 points, placing the O1 IOI system in the 49th percentile of competitors, illustrating the limits of human-designed clustering within these specific contest rules. The critical question is what happens when you remove that human-engineered pipeline entirely and instead scale the reinforcement learning and inference-time compute. This chart shows model accuracy on the 15-question, 3-hour AIM math competition. The left plot indicates that increasing training compute yields linear performance gains. Providing more compute at inference allows the model to autonomously explore deeper logical branches. When researchers evaluated the O3 model on the identical IOI 2024 problems, they discarded the subtask-specific prompts and the complex clustering pipeline used for O1 IOI. O3 used a simplified approach. It generated 1,024 samples from a single prompt and selected the top 50 based purely on internal test time compute scores. Without a handcrafted selection strategy, O3 scored 395 points, surpassing the competition's gold medal threshold. The scaled general-purpose RL model outcompeted the heavily engineered domain-specific pipeline by internalizing the search process. If O3 isn't using human-coded clustering pipelines to verify its 1,024 generated solutions, we must look at how it is checking its own work. The answer is self-imposed validation. This is the emergent ability of an RL-scaled model to dynamically write its own verification tools on the fly. This Python script, autonomously generated by O3, tests its own primary algorithm. To establish a baseline, O3 writes a secondary brute force solver. It then generates random test cases, runs them through both solvers, and executes a cross-check to catch any discrepancies before submitting. No human prompted the model to write a brute force checker. This verification strategy emerged from end-to-end reinforcement learning. Scaling test-time compute gives the model the space to construct, execute, and evaluate its own internal scientific method. The true test of these capabilities is whether this autonomous reasoning applies to massive, multi-file codebases in production environments. The HackerRank Astra dataset simulates actual software development tasks using modern web frameworks like React, Node, and Django. Using the same self-validation loop, hypothesizing a fix, writing a test, checking the output, the O1 models hit a 63.9% first-attempt pass rate on these repositories. A more rigorous test is SWEV-BEV-SPENFIED. This is a dataset of 500 validated, real-world GitHub issues that directly tests an AI's ability to navigate and patch actual production code. This chart illustrates the scaling jump in performance. As we move from the O1 architecture to O3's scaled RL, the success rate on production code jumps from 33.2% to 71.7%. The ability to autonomously generate brute force verifiers in an IOI puzzle is the same cognitive mechanism required to autonomously trace and patch a bug in a web framework. Right now, we are witnessing a transition from rigid, predefined pathways to self-correcting neural processes operating across vast architectures. The results indicate a transition from explicit symbolic reasoning wrappers toward implicit, learned reasoning mechanisms. The data suggests that the era of AI engineers manually writing search trees, heuristics, or clustering pipelines to squeeze performance out of language models is ending. The path to elite reasoning in science, math, and coding lies in scaling reinforcement learning and inference-time compute. In this framework, artificial reasoning develops when a model is given the capacity to ruthlessly interrogate its own wrong answers.